Good morning. Welcome to the webinar, the Evolving CO2 Market. My name is Caroline Genesi. I'm the Lux Account Manager for ExxonMobil, and I'll be moderating our session. Presenting today is my colleague, Runeel Daliah, Senior Analyst here at Lux Research. Throughout the webinar, you can type any questions that you have in the questions box on your screen. Time permitting, we will answer all the questions that we can. If your question does not get answered, please do not hesitate to email it to questions@luxresearchinc.com and we will respond. Before we start, I just want to give a little PSA announcement that now from May 18th, any ExxonMobil employee can have a license to the Lux Intel platform to access the research and insights that Lux has to offer. If you're interested in this complimentary trial, please let us know in the questions box on your screen. And at this point, let's jump into the presentation. Runeel.
Thank you. Thank you very much, Caroline, and hello to everyone. It's good to be here today. As Caroline mentioned, my name is Runeel Daliah, and I am a Senior Analyst on Lux Research's Energy Transition Service. And within that service, I lead our coverage on the decarbonization of the industrial sector. So looking at various heavy industries like steelmaking, oil and gas, chemicals, cement, and so on, and looking at how these industries can achieve carbon neutrality. Now, as part of that coverage, as you can imagine, CO2, carbon capture, sequestration, utilization is a very important technology. It's a very important tool for these industries to decarbonize, which is why today we wanted to provide you with an overview of our coverage on the CO2 space. So for the sake of this presentation today, we will cover the entire CO2 supply chain, and we will highlight the key innovation and the key trends that is driving the adoption of CO2-based technologies across the energy sector. So we'll first start with looking at very briefly at the drivers for the carbon capture and utilization space, and then diving in deeper into carbon capture technologies, the logistics of storing and transporting CO2, as well as the utilization of that CO2 into different products. Now, starting with the drivers for CCUS. Now, the main driver for any carbon capture, utilization, and sequestration technology is, of course, carbon pricing. Now, carbon pricing is available all over the world, and you can see on this figure here, different countries and their carbon prices. Now, the carbon price takes two forms. You can take the form of a carbon tax, where you are penalized by the amount of CO2 that you're emitting to the atmosphere, or you can take the form of a market, where you're trading carbon credits onto the market based on the offsets that you require to neutralize your CO2 emissions. Now, what you can see from this figure is that there is no general carbon price around the world. The carbon pricing mechanisms globally is very fragmented by countries, and in the case of the US, sometimes even by states. And you can see that today, the average carbon price is quite low. It's at around $20 to $40 per ton of CO2. There are some outliers out there, like Sweden, for example, or Switzerland, that have a carbon price of above $100 per ton of CO2. But what's important to see here is the fact that large industrial nations, for example, the US, Canada, or China, or Japan, or Korea, these are the countries that emit a lot of CO2. And you can see here that the carbon tax in those countries are still quite low. Now, looking deeper at the carbon pricing mechanisms around the world. The first one is the emission trading scheme, cap and trade system, which is currently present in the EU today. So this is essentially a mechanism where you can trade carbon credits on a market. So if you have offsets available, you can sell that to companies that are emitting CO2 so that they can offset their emissions. So this scheme has been around for many years now, and what we're seeing is that the price of the carbon credit has really gone up over the past year. So in 2020, there were 1.6 gigatons of allowances that were sold onto the market. And as recently as 2 days ago, the price of one of these allowances is at around 90 euros per ton of CO2. So you can see that this price fluctuates, which is good because it does allow the market to adjust based on the amount of allowances available. But what's I would say the disadvantage about this scheme is that it does not provide stability, and that's really what's required when it comes to carbon capture technologies in particular, because carbon capture technology is not economical unless you have a high carbon tax. And the fact that the carbon price in the EU varies from 50 to 90 or even sometimes less than 50 euros does not provide much stability for companies to deploy carbon capture, utilization, and sequestration technologies in the region. On the other hand, you have the 45Q system in the US. So this is a much more stable mechanism where you have a fixed price allocated to the CO2 that you capture as well as sequester. Now that mechanism has been around in the US for a couple of years now, and is really driving the interest in carbon capture deployment in the country. Now, it is a stable mechanism which provides stability for project developers, but the mechanism is also very restrictive. It only applies to carbon capture and sequestration and utilization technologies. So if you have a technology that can offset your CO2 emissions, that can abate your CO2 emissions, but it is not a carbon capture technology, then it would not qualify for the 45Q incentives. So there is a middle ground when it comes to adopting policies to incentivize the carbon capture technologies. One, you need the stability, but two, you also need to be open to different technologies, so not limiting yourself to carbon capture incentives specifically, but really open to any technologies that will allow you to reduce your emissions and provide a credit for every ton of CO2 that you abate. But with the energy transition, and with many companies around the world announcing carbon neutrality targets, we're now starting to see much more activity in the carbon capture, sequestration, and utilization space. Now, one example of a country that is really driving forward the industry is the UK. Over the past few years, the UK has announced many projects looking at deploying carbon capture technology, but also sequestrating the CO2 underground. And on this slide here, you can see a number of these projects. Now, these carbon capture facilities will be deployed at industrial clusters. So these are the clusters that emit a lot of CO2. And in an attempt to reach the goal of carbon neutrality, the UK is looking towards carbon capture technologies to neutralize the carbon intensity of these clusters. So currently, all of these projects are in development. They're applicable to a wide range of industries. You have chemical facilities that will deploy carbon capture. You have blue hydrogen facilities that will also be built to provide low carbon hydrogen to chemical and the fuel sector. Another country that is also driving forward development in the carbon capture and storage space is the Netherlands. So the Netherlands had 3 projects known as the 3 Musketeers, Porthos, Athos, and Aramis. But the 3 projects were about capturing the CO2 and then sequestrating that CO2 into the North Sea or into depleted gas fields. So these projects are currently in development with the exception of Athos. So Athos was announced a few years ago, and the goal of the project was to capture CO2 from a steel plant and to sequester the CO2 to the ground. Now that steel plant is operated by Tata Steel, but recently Tata Steel decided to forgo carbon capture technology to decarbonize its steel making process and to instead use low carbon hydrogen. So that project right now is no more, but Porthos and Aramis are still active and still in development. So what you can see here is that These projects are not a single carbon capture project attached to one single facility and sending that CO2 to one single pipeline. It's a collaboration between many companies. In this case here, it would be the ports in the Netherlands, whether it's the port of Rotterdam or the port of Amsterdam, together with the industrial players. And that's very important because when it comes to carbon capture and sequestration, it's a very capital intensive endeavor, which is not possible for one company to completely own themselves. So it requires collaboration with government entities as well as corporations. Now, diving a bit deeper into the technologies that will form part of these different projects. So first, looking at carbon capture technology. Now, carbon capture technologies, there are two ways to categorize these technologies. The first way is by looking at the application of the carbon capture technology. So one way to categorize it is by splitting the application from pre-combustion, which is about capturing the CO2 before you combust the natural gas, for example, to post-combustion, which is capturing the CO2 after you combust the gas or the coal. And then you have direct air capture, which is about capturing the CO2 directly from air. But you can also categorize carbon capture technology by the type of material used to separate the CO2 from the gas. And these are solvent, solvents, and membrane. Now, how do you separate carbon capture technology by application? The key factor here is really looking at the concentration of CO2 in the flue gas. And this is very important because the cost of carbon capture is highly dependent on the concentration of CO2 into the gas that you're trying to separate it out from. So in the case of pre-combustion, over here, the concentration of CO2 is typically quite high, from 50% to 90% if you're capturing that CO2 from an ethanol or a fertilizer plant. Now, this is why today carbon capture from ethanol and ammonia plants are commercial. It's already been done commercially because capturing the CO2 there is quite cheap. But then you get into post-combustion carbon capture. This is where most of the projects are focusing on. So this is about capturing the CO2 after you combust the natural gas, or after you combust the coal in a steel plant, for example. And the challenge here is that the CO2 in that flue gas is at a very low concentration of 5 to 15%, which means that you need a lot of energy to concentrate that 50% CO2 into a 100% pure CO2 stream. So here, I don't want to give a fixed number to the cost of carbon capture because it's really dependent on the size of the facility, the concentration of CO2 going into the carbon capture unit, the efficiency of carbon capture, and so on. But you're generally looking at costs of from $80 per ton of CO2 to $150 or $200 per ton of CO2. And then finally, you have direct air capture. So direct air capture is about separating the CO2 directly from air and concentrating that into a pure stream. Now, there's not a lot of CO2 in the air. It's a very, very low concentration, which is why direct air capture technology is today very expensive. It's a very expensive source of CO2. Now, estimations are out there with the cost of direct air capture technology. Lux Research has spoken to all of the technology developers in the direct air capture space, Climeworks, Carbon Engineering, and so on. And based on our estimations, direct air capture technology is at around $300 to $400 per ton of CO2. But again, this is highly dependent on the size of the facility, the location, and the amount of energy required for separating that CO2 out. In terms of technology, there are three main groups of technology for CO2 capture. The first one is solvent. Solvent is today the only commercial technology available for carbon capture. It is today commercially deployed at scale in the post-combustion facilities. It's about using a liquid medium for separating the CO2 out of the flue gas. And then you have solvents, which is about using a solid material for separating that CO2 out of the flue gas. And that solid material can vary. It can be an amine coated ceramic, for example, or it can even be a metal organic framework. So today, solvent technology is currently in development. One company in Canada called Svante is advancing and will be the first one to deploy a commercial scale facility, but generally the technology is at the pilot scale. And then finally, you have membrane. Now, the advantage of using a membrane for carbon capture is that it's a very, on paper, a very simple system. There are no moving parts and so on. You don't need a high temperature to separate the CO2 out of the flue gas. But currently, membrane technology for carbon capture is at a lab scale. It's very hard to scale up the technology because the challenge here is about manufacturing large membrane sheet for carbon capture deployment. And right now, the technology is at a lab scale with little prospects for commercial deployment in the next decade. Now, carbon capture is a very vibrant space of innovation. There are many companies out there active in the carbon capture space, from large corporations like oil and gas companies or Siemens or BASF, for example, to startups and research institutions. And what you see here is a snapshot of the major players in the carbon capture space today, categorized by the type of technologies that they are developing and deploying. So solvent, being the commercial carbon capture technology today, is the most active in terms of technology developers. And over here, you have large corporations like Mitsubishi that have already deployed their technology at scale, but you also have startups like Carbon Clean, for example, that is right now, or Sea Capture, that is right now developing new type of solvents, new types of amine solution or non-aqueous amine solutions that they claim reduces the cost of, reduces the energy consumption of carbon capture, which in turn reduces the cost of the entire system. And then you have sorbent technology. Now, as I mentioned before, sorbent technology is currently in development. Svante, the Canadian company, will be the first one to deploy that technology at scale at a cement facility in the US in the next 5 years. But otherwise, you have some promising companies in there like MAF Technologies, Climeworks, and Mosaic Material that are all developing solid material for carbon capture. And as for membrane, it's a very sparse innovation landscape today when it comes to carbon capture. Some promising companies like Air Liquide and Fuel Cell Energy, but unlikely to scale in the next few years given the challenges of using membrane for large applications of carbon capture. Now, we won't have the time to go through all of these technologies in detail, but what I wanted to draw your attention to is the solvent space. Now, the assumption with solvent is that it is a commercial technology and there's not much innovation potential left in this area. But the reality is that there's a lot of innovation potential left, and you have companies innovating in the space. Now, the main solvent today used at a commercial scale today is the monoethanolamine solvent, which you can see on there that the energy consumption of that solvent is between 3 to 3.5 gigajoule per ton of CO2 captured. Now, there are disadvantages to using the ammonia-based solvent. You have a high energy requirement, but you can't also use that solvent in the pure state in the carbon capture unit. You have to dilute it in water to concentration of around 30%, which means that you have a carbon capture system, but you have 70% of that space is filled with water, which does not do anything for carbon capture. So you have a large system and you have an inert material being circulated around the system. So these two areas, the dilution as well as the energy consumption, are the areas that companies are trying to tackle with new solutions. One of these new solutions is the secondary amine, which is an improved amine solvent that companies claim can reduce the energy consumption of carbon capture. So you have companies that have already achieved an energy consumption of around 2.3 to 2.5, but we are also aware of companies that are already reaching an energy consumption of around 1.8 to 2 gigajoule per ton of CO2. But you also have companies developing technologies known as non-aqueous solvent, where you don't need to dissolve the carbon capture solvent in water, which means that you're capturing the same amount of CO2 with a much smaller system and a lower energy consumption. And then finally, you have a more niche approach, which is doping a solvent with enzyme, and the enzyme accelerates the absorption of CO2. So today you only have one company developing this technology. They used to be known as CO2 Solutions in Canada. They were recently acquired by Saipem last year. But what this is showing here is that you have potential for innovation in carbon capture, and the goal is really here to reduce the energy consumption of carbon capture. Now, one of the companies innovating in the space, one of the startups active in the space is Sea Capture, based in the UK. Now, Sea Capture, they are a startup developing a non-aqueous solvent for carbon capture. We spoke with the company, we spoke with the CEO of the company, we profiled the company, and according to the company, they can already reach an energy consumption of around 1.5 to 2 gigajoule per ton of CO2 with their non-aqueous solvent. Now, these claims have not yet been verified at scale because the company today is only at the pilot scale. It's deployed a pilot unit at the Drax power station in the UK, and currently they don't have plans yet to commercialize a very large scale unit yet. So they're still in the process of validating that technology at this pilot scale and eventually raising the funds for a much larger facility. But they're one of the few startups in the space that is actively developing a non-aqueous solvent. So it is worth monitoring this company. Another interesting startup in the space that was recently acquired actually by Baker Hughes is compact carbon capture. Now, the vast majority of technology developers in carbon capture focus on developing a new type of solvent or sorbent for carbon capture. Compact carbon capture takes a different approach where instead of focusing on the solvent, they focus on the carbon capture system itself. And the company has developed a technology that allows for small-scale carbon capture. So you could potentially deploy this unit at an offshore rig, for example. Now, the company is solvent agnostic. Another advantage of the technology is that you could potentially use one of the new solvents from Sea Capture or from one of the other companies out there to essentially combine the benefits of a small-scale system with the low energy consumption of a new solvent. Now, according to the company, they can reduce the size of a carbon capture unit by over 90%, which will lead to a significant reduction in the capex of the system. Now, they deployed this technology at a pilot scale last year, and they were acquired by Baker Hughes in November 2020, and they don't have plans yet to start building a large commercial facility. They're currently still at the demo scale, but we expect a commercial unit to be up and running in the next 5 to 6 years. So this was a brief snapshot of two interesting companies developing technologies in carbon capture. The reality is that you have many other companies out there in the space, and what you see here is known as the Lux Innovation Grid. This is our assessment of startups in the carbon capture space, where we speak to the company and we rank them based on their technology, as well as the ability to execute on their business strategy. And you can see here that most companies today are in the left quadrants. So companies today either have a technology that is not yet ready to scale, that still requires development, or they have a technology that is ready to scale but is struggling to get to that next step because of a lack of funding or a lack of partnerships. Some companies are standing apart from the competition. One of them is Svante, the Canadian company that has partnership with oil and gas and cement companies, so they're actively deploying the technology at scale. But you also have other companies like Sea Capture or Carbon Clean, for example, also advancing to the commercial scale. So the next 5 to 6 years, we expect this grid to become much more crowded because there's a lot of innovation happening in carbon capture, but you also expect the space to be more differentiated. Companies will become dominant while some of the companies will be unable to proceed to the commercial scale. So this was an overview of our coverage on carbon capture technologies. Now, when looking at the carbon logistics, so the logistics of storing and transporting CO2, so over here, this is much less about innovation. It's more of a question of deployment. So once you capture the CO2, you have to transport it to its sequestration site or to its utilization site. And there are various ways of transporting CO2. Today, the best approach for transporting CO2 is by using pipelines. Now, even in the pipeline space, you have different modes of transportation, and you can see those here on this slide. You can transport the CO2 as gas, you can liquefy the CO2, or you can utilize dense phase or supercritical state transport. Now, all of these are about transporting CO2 in the pipeline. What you need to look at is really the chart on the right, which is about looking at the state of CO2 according to the temperature and the pressure. Now, once you capture the CO2 and you need to send it to its sequestration site, its utilization site, the best way would be to match the pressure of that end use together with your pipeline. So if you're looking at a high pressure transport, then you're essentially operating in the dense phase or supercritical fluid region. And you can see that the temperature scale, it doesn't take a lot for CO2 to get to the dense phase or supercritical fluid region once you reach a certain amount of pressure in your pipeline. So today, there's not much CO2 being transported around because there's not much use for CO2 other than in the beverage industry. But in the future CO2 economy, once you fully realize the sequestration as well as the utilization application, there will be a need to transport large amounts of CO2. And the form of transportation will most likely be in the dense phase or supercritical state, depending on where you are in the world. But pipelines is not the only way to transport CO2. What we're also seeing is innovation, developments in ocean-based transport of CO2. And you can see two such projects here. The first one is about transporting the CO2 in a solid form, so in the form of dry ice, but also in a liquid form. Or you can transport CO2 in maritime carriers as well. Now, what's the goal of CO2 transportation via ocean? Now, if you are, say, a country like Japan or Korea, where you are emitting a lot of CO2 that you need to capture and sequester, but you don't have a lot of space or any space to sequester that CO2 because you don't have the geographical features to store that CO2 underground, then you need to find a sink for that CO2 outside of your region. So this is why developments like these are very important, because it will allow nations or industrial regions that do not have access to sinks for the CO2 to essentially transport their CO2 emissions and sequester it somewhere else. But again, this is currently at a very early stage. We are not yet at a point where we need to transport large amount of CO2 over ocean. So this will take quite a while before you get that full scale supply chain. Now, once you transport the CO2, you can start to either sequester the CO2 or use it to make a product. So looking at CO2 sequestration. Now, there are many different sinks for CO2. One of the preferred approach is to utilize oil wells for CO2 sequestration. So what you see here on this slide is a figure from the Global CCS Institute, where they look at the potential of CO2 sequestration in oil and gas fields. And you can see that regions like the US, Canada, Europe, Russia, and so on have a lot of potential resources to store the CO2. Now, these regions are large industrial nations, which means that they are lucky in a way because they have a sink for the CO2 at hand. But if you look at countries like Japan and Korea, which I spoke about earlier, but also Southeast Asia or India, for example, large industrial nations that are high emitters of CO2, you can see that they don't have access to a source of a sink for their CO2. So this is why technologies like ocean-based transport of CO2 is very important. Now, looking at the oil and gas fields for CO2 sequestration. Now, it's not a matter of simply pumping that CO2 down to an oil and gas reservoir, because you need to prepare that oil and gas reservoirs, and not all of them will be suitable for CO2 sequestration. Now, on this slide here is different considerations that should be looked at when assessing the suitability of an oil and gas well for CO2 sequestration. Because not all oil and gas wells are equal. They have different operating conditions, they have different requirements for remediation, and they have different integrity as well. So when assessing these oil wells, these all need to be taken into account. And there are various technologies that will allow you to do so, various expertise at hand for an oil and gas company especially that will allow them to do so. So not all oil and gas wells will be able to take in CO2, which means that you may need to look for alternative sinks for that CO2. Now, sequestrating the CO2 is one thing, but you also need to make sure that once the CO2 is sequestered, it stays there indefinitely. And this is currently a point of contention for many opponents of CO2 sequestration. They often say that CO2 will eventually leak back into the atmosphere. Now, there are ways to mitigate the leak of CO2 once it's sequestered underground. There are technologies that will allow you to detect the CO2 leaks. Now, today, there is a very big industry that revolves around methane detection. And on this slide here is a snapshot of the different companies that are developing and deploying technologies for methane detection. You have aerial-based detection technologies as well as ground-based detection technologies. Now, for most of these developers, they can adapt their methane detection system to detect CO2 as well. It's not a very challenging thing to do. There are companies that are already doing that. For example, GSG Sat or Bluefield, for example, have already shown that they can adapt their methane detection system to detect CO2 emissions as well. But unlike methane detection, it's not enough to just detect the CO2. You also need to make sure you also need to know how much CO2 has leaked into the atmosphere. And this is again a challenge for any of these technologies. Once you detect a CO2 leak, you also need to be able to quantify that CO2 leak. And this is very important because this goes back to the carbon credit system. The carbon credit system is a quantitative system where you essentially, I apologize for this, where you're essentially trading carbon offsets onto the market. Now, if there's a leak of CO2 in your operations, you will require carbon credits, to offset those emissions. So it's very important to be able to quantify the amount of CO2 that is coming out of your facilities or coming out of your sequestration facilities. Now, finally, looking at the last sector in the CO2 supply chain, which is about using the CO2 to make a product out of it. So in many cases, if you say, for example, you don't have the required carbon taxes to make the business case for sequestration work, or if you simply don't have the sinks for CO2 sequestration, one other avenue for CO2 is to simply convert it into a product. Now, CO2 utilization is an area that is rich, very rich in innovation. And today you can make 6 types of products from CO2. These are concrete, chemical, fuel, polymer, carbon, and protein. So these technologies, these product categories, all use various different technologies, from chemical technologies to catalytic technologies or electrochemical technologies or even biological conversion to convert the CO2 into a product. They also all at the various stage of development. For example, concrete and polymer are both commercial already, whereas chemical fuel are currently at the development stage. Now, as an oil and gas company, you emit a lot of CO2. So when looking at these product categories, if you were to say invest or develop one of these categories, you want to develop a category that can absorb a lot of your CO2 emissions. Now, one such category is the concrete industry. Now, in the concrete sector, the utilization of CO2 is relatively straightforward. You don't need any high temperature. You don't need any catalyst. It's simply a matter of reacting the molecule of CO2 with calcium oxide to produce calcium carbonate. Now, there are 2 ways of doing so. You can simply react the CO2 with a waste material that contains that calcium oxide to produce a calcium carbonate, and you then use that carbonate as an aggregate, which you mix with cement and water to produce a concrete. Or you can use the CO2 as a curing agent, where over there, you're injecting CO2 into the wet concrete mix to form nanoscale calcium carbonate particle into the concrete material, which reduces the curing time, but as well as increase the strength of the concrete product. Now, depending on the application, you have a range of CO2 absorbed. from 0.1% current application to up to 40% for aggregate production. Now, the technology is commercial, and there are several advantages with using CO2 in a building application, building material application. In the case of curing, as I mentioned earlier, the resulting concrete product that has been cured with CO2 has a higher compressive strength, which means that with the use of CO2, you have a performance advantage. You have a product that's stronger than the incumbent. And that is very important because this is the only application of CO2 where you actually have a performance differentiation. If you're making a fuel or a chemical like methanol from CO2, that fuel or that methanol would be chemically and physically identical to fossil-based methanol or fuel. Whereas here you have a different product, you have a performance advantage, which means that with a concrete product, you can actually command a premium on the product because you're selling a better performing product onto the market. And that premium can then offset the cost of CO2 utilization. Another advantage, and that's applicable to both curing and aggregates, is the fact that once the CO2 is converted into a calcium carbonate, that CO2 is locked away indefinitely. So there will not be any release of CO2 further down the supply chain, unlike the case of fuels or chemicals, where once you burn the fuel, that CO2 is released back in the atmosphere. So you're essentially transferring your scope 1 emission into a scope 3 emission, and the same thing for chemical as well. Eventually, that chemical, that polymer will degrade and will release that CO2 back into the atmosphere. But just because it's commercially validated does not mean that it's easy to deploy this technology, because there are quite a few barriers in the use of CO2 in the building sector. The first barrier is, of course, the lack of policies that are incentivizing the adoption of this technology. And this is very unique to the concrete industry, where they are quite conservative to any new type of innovation, mostly for safety reasons. Now, because the concrete product that you're producing has been made in a different way than the incumbent process, every concrete product made from CO2 will need to be approved. And that approval process can take a very long time, and it also varies by location, by country, but also by state, at the state level as well. And this is really a major roadblock to the to the widespread deployment of this technology at scale. Now, another product area is the chemical sector. Now, you can make a chemical from CO2, and there are various chemicals that you can make from CO2 with an array of different technologies, thermochemical, electrolysis, or biological technologies. One of the main chemicals being looked at today is methanol. So you make methanol by reacting the CO2 directly with hydrogen over a solid catalyst. But you can also make other molecules like ethylene, for example, or carbon monoxide from electrolysis. So there's a wide range of chemical that you can make. And depending on the type of chemical that you make, you're either you're absorbing from 1 to 1.5 ton of CO2 per ton of chemical. Now, making the chemical from CO2 is quite challenging. The technologies are not simple, and it's also very energy intensive as well. And this is really a major barrier to the widespread commercialization of that technology. So in the case of methanol, for example, the technology has been validated at the deeper scale for more than a decade now, but it hasn't been successfully commercialized because methanol from CO2 and low carbon hydrogen is much more expensive than methanol from natural gas. So to be able to sell onto the market, these developers really need to have the policies in place to incentivize adoption of low carbon chemical into the market. Now, the chemical industry today, despite the momentum in decarbonization, does not yet have the necessary policy mechanism for the adoption of low carbon chemical. Unlike the fuel sector, where you have the RFS, the LCFS system in the US, as well as the RED II system in Europe. So for the chemical industry, you will need a similar type of regulatory mechanism to incentivize the adoption. The other thing with chemical is that you need a source of hydrogen. Now, if your goal is decarbonization, then that hydrogen has to be low carbon in nature. So either blue hydrogen or green hydrogen. And again, it's a question of cost. Blue and green hydrogen are more expensive than hydrogen from natural gas, gray hydrogen. So again, you need to have policies in place for the adoption of low carbon hydrogen in the chemical sector, but also in other sectors to incentivize the build out of the hydrogen economy. And finally, the last category for large-scale utilization of CO2 is the fuel sector. So over here, you can produce two types of fuel. You can produce gaseous fuels like methane from CO2 using a Sabatier reaction, or you can produce liquid hydrocarbon fuels like diesel, for example, via Fischer-Tropsch technology. So over here, the utilization potential of fuel is quite high, from 3 to 6 tons per ton of fuel produced. But what is worth keeping in mind is that those emissions will be released back into the atmosphere eventually. So making the fuel from CO2 is not a tool for decarbonization, because you're essentially converting your Scope 1 emission into Scope 3 emissions. It will lead to decarbonization on a global perspective, because recycling the CO2 back into fuel removes the need for fresh hydrocarbon feedstock, but it is not a tool for a company to decarbonize its operation. Now, the technology today is at the early stage, at the pilot and at the demo scale. The first commercial facility is set to come online in the next 5 to 6 years. You have a few companies working on that, Sunfire and North Sea Fuel in Europe, but you also have companies in the US that are looking at converting CO2 into a liquid hydrocarbon fuel. Now, in that space, synthetic fuels are lucky that they can leverage the regulatory promoters that are already present for biofuels, both in the US and in the EU. Now, these fuels are sometimes not fully approved yet in these systems, but the mechanism for approval is already here. So once large volumes of that fuel come onto the market, we expect the regulatory system to be adapted as well. But again, especially in the case of fuels, it's all about the question of cost. Right now, making a fuel from CO2 and hydrogen is very expensive. Based on our internal analysis, it's around 5 to 6 times more expensive with low crude oil prices. And for them to be able to compete, you really need to have these credits in place to offset that high cost of production. So to summarize the CO2 utilization space, you can see here the Lux innovation grid for CO2 utilization. You can see the amount of companies active in this space. And we actually ran out of space, so we're not showing you all the companies, but just a snapshot of companies in the fuels, in the chemical, as well as in the building material industry. So there's a lot of potential for collaboration. There's a lot of potential for acquisition. You can see that most of these companies right now are still very early stage when it comes to business execution. Some of these companies are already advancing to the commercial scale, for example, Carbon Cure or Sunfire in the EU, Ineratech, Solidia, and so on. But there's many companies out there with strong technologies that are currently still looking for partners, looking for funding to be able to scale the technology to the commercial end. So this is really an opportunity for a large corporation like ExxonMobil, for example, to enter the space by collaborating with these companies or simply acquiring them. Now, to summarize the presentation, what is our opinion of the CO2 value chain? I think that everyone will agree with us here that you need carbon capture to meet the goal of the Paris Agreement. We will never be able to decarbonize without carbon capture, sequestration, and utilization technologies, because there will always be CO2 emitted, most likely not as much as we are doing today, but there will always be permanent sources of CO2 emissions in the chemical sector as well as the cement sector, for example. So you need to have carbon capture technology and sequestration resources to be able to reach net zero emissions, which means that you need the policies in place to develop the market. Now, carbon capture technology is commercial in the sense that it is commercially ready to be deployed at scale, but right now the policies are not strong enough to actually incentivize adoption of these technologies. So you need to have stronger carbon taxes, but also a more resilient regulatory mechanism to provide stability to companies looking to deploy the technology and ensure that they have a secure market for deployment. once you have these policies in place, once you have these high carbon prices, then adoption of carbon capture, sequestration, and utilization will follow. And three, it's really about identifying the opportunity. Now, an oil and gas company is very well placed to succeed in the CO2 supply chain because the expertise that oil and gas companies have when it comes to upstream, midstream, and downstream can be used to develop the CO2 supply chain. Now, of course, oil and gas companies are already active in the space. So ExxonMobil, for example, is a big player in the area, as well as the European oil and gas majors. But this is really an area where oil and gas companies will really have a pivotal role to play in the space. So without investment, without development from oil and gas companies, it is unlikely that the carbon capture space will succeed in the future. So this was an overview of our coverage on carbon capture, sequestration, and utilization. What you see here is a snapshot of what you would have access to in our coverage. We have a lot more content on the space, a lot more company activity that we monitor, a lot more developments that we keep an eye on. So this is a taste of what you would get with a subscription with Lux Research on carbon capture, utilization, and sequestration. Caroline, I'll pass it over to you to conclude, and if there's any questions, I can also address them.
All right, thank you very much, Runeel. Great job. And yes, this is just the tip of the iceberg. So if you don't have access, you are welcome to have it until May the 18th. Just type into the questions box and we'll get you set up. We're going to take a few questions. We had quite a number of questions, so if we don't get to your particular question on the call, I will be in touch with you after the webinar. So Runeel, we have here, what is the timeline for the Dan Unity CO2 carriers to be available?
Can you repeat the question, please? What is the timeline for
the Dan Unity CO2 carriers to be available?
Let me see. I don't think I. Is a question written on the?
Yeah.
I think I can address that separately. I would have to look into that. The Dan Unity CO2 carrier. Yeah.
Okay.
I can say if it's about a project, then yes, I will have to look at the project in more details. But based on our last assessment, we expect that project to be concluded by the end of the decade. Right now, the momentum in development of that project is quite slow because there isn't yet a big market driver for the international transport of CO2. But I can follow up on this question and provide a more specific timeline for it.
Okay, thank you. Thank you. Okay, here's another one. How do you see the carbon capture space evolving in terms of technology development? Will solvent remain the dominant technology for capture?
I want to say yes to that question. I mean, at the end of the day, solvent has been validated at scale. The MES solvent has been validated at scale. The systems to handle the solvents are also well known and deployed at scale. Now, there's always place for innovation. You could potentially use a solid absorbent, for example, for carbon capture, but that technology would essentially compete with solvent for the same large-scale application. And if you look at the timeline, right, carbon capture technology, people are ready to deploy the technology, which means that once the regulatory policies are in place to incentivize adoption, companies will not be willing to wait 5, 10, 15 years for a solvent to be developed and validated at scale. They're looking at making investments now, which means that they will be looking at a technology that has already been proven, which means that solvent will most likely get the largest market share of that carbon capture market in the future. Now, there are advantageous to solvents. If you're looking at direct air capture, for example, if you're looking at smaller scale application, then solvents have an advantage over solvent given the smaller system size. But again, this is a question of what would be the best application and how to match the technology, the capture technology, to that specific application.
Thank you. Here's one more here. What would be the role of direct air capture fit in the broad energy transition?
Yeah, I didn't really elaborate on direct air capture. Direct air capture is interesting because there's a lot of activity behind direct air capture today. I believe there's more than 10 companies active in the space. So there's a lot of money going into VC funding going into direct air capture technology. Our opinion is that direct air capture is a technology that is currently overhyped in the sense that it is a technology that we need, but not a technology that we need today or in the near future. Now, the goal of decarbonization is not to capture CO2 from air and bury it underground. It's about avoiding the emission of CO2 in the first place. Now, we see companies moving in that direction as well. When it comes to decarbonization, they are really looking at technologies to abate their CO2 emission. But you will never be able to completely eliminate CO2 emissions from your supply chain because it's simply not realistic to do so. So we see direct air capture really as an accounting measure. Once you manage to eliminate as much CO2 emissions as possible from your facility, you will always have a small streams of CO2 emissions where it's simply not possible to capture and sequester somewhere. So then you offset those emissions with direct air capture technology, which means that direct air capture technology is commercial. It's been proven to work at scale by Climeworks in Iceland, for example, but it's not a technology that companies should be investing into right now. This is a technology that they should be really looking at deploying by 2035, 2040, once they reach the goal of carbon neutrality, and they need to offset those remaining emissions. So yes, lots of development in direct air capture, but we expect the industry to cool down once people realize that direct air capture is a very expensive way of offsetting your emissions.
Thank you. And there's another one here going back to the solvent space, and it's non-amine solvent-based carbon capture. For example, Selexol has been around for a long time. What is new and different in the non-amine solvent development, like sea capture?
So it's nothing drastically different. It's really about eliminating water from the carbon capture solution. Now, with many of these technologies, with not just non-aqueous solvent, but many of the novel carbon capture technologies, many of them have been around for years now. They've been developed at the lab scale, the pilot scale for years now. The reason why they haven't been deployed at scale is not because the technology itself was not ready for commercialization, it was because the industry wasn't ready for commercialization. So what happened is that many of these companies developing these technologies essentially tried to go to the market that did not have a carbon tax, so there was no interest from the industrial emitters to deploy carbon capture. And due to the lack of funding and development momentum, many of these companies failed. So technology from sea capture is not drastically different from the Selexol technology. It's just a matter that sea capture has entered the space at a time where there's a lot more momentum in decarbonization. But there's many examples of that where companies have failed because of a lack of funding and development momentum, even though they had a relatively good carbon capture technologies.
Thank you. And let's see if we have time for just one more, to squeeze one more in before the end. Which CO2 utilization is best? How do you assess CO2 utilization technologies?
Right. So there's no fixed answer to that. It's really a question. It's really a scenario, right? I mean, if you're really looking at decarbonization, if your goal is to decarbonize your operations, obviously you wouldn't want to convert that CO2 emission to a fuel which will be burned and release that CO2 back in the atmosphere. So if your goal is decarbonization, then you really need to only look at products that can lock away your CO2 indefinitely. And today that's just the concrete sector. Now, if your goal is to develop a new business and you're an oil and gas company who's already operating in the oil and gas business, of course, then fuels or chemicals are a good starting point for you to enter the CO2 utilization space, because you're producing the synthetic fuels and you can then leverage your existing infrastructure, your existing capabilities to send that fuel onto the market. Now, if you have an operation where you only have small amounts of CO2 emitted, so I'm thinking here of like offshore operations, for example, where you won't need to convert a lot of CO2 into a product, then you would focus on products where only small scale operations make sense. So that could be, for example, again, the concrete industry, but you can also look at protein sector, for example. A protein reactor, a microbial reactor for protein manufacturing is quite small compared to a fission reactor for synthetic fuel production. So it really depends on, it's a really question of economics. How willing are you to sell a product that is much more expensive than the incumbent product onto the market? It's a question of how close are you to the market that you're targeting. So if you're already in the fuel business, then synthetic fuels make sense. But it's also a question of capacity. You know, if you have a lot of CO2, then you only focus on products that can absorb that CO2 into the market. So it's really, if you're looking at a specific utilization product area to enter, you really need to take all of these into consideration.
Well, thank you. Thank you. And thank you everyone for attending this webinar. Our next exclusive for ExxonMobil webinar will be on St. Patrick's Day. And it's going to be at the same time, 10 o'clock Central, 11 Eastern, on Recycling Outlook, the Road to 2025. An invite to register will come out shortly. You will get this slide presentation and the recording from today. It will be sent to everybody. And after leaving the webinar, we'll be sending out a short survey. We appreciate any feedback you give to us. It helps us inform and improve future webinars. So thank you all for joining. Have a great day, and we will talk soon. Thank you.
Thank you very much.